this skill that is about linear regression. Here's the text of the skill. So this all has to do with scatter plots and interpreting the output of a linear regression technology platform like ArtofStat. And so we're going to use this data from an NIH study that looked at the relationship between exercise and hospital visits in people who are 65 and older. And so when we look at this data, we see that how many hours in the year they tracked over the course of the year did the person, the patient, spend doing resistance training, and how many hospital visits they had. So you can see some people had a lot of hospital visits and other people had very few hospital visits. So if I was going to analyze this, I want to think what's the explanatory variable and what's the response variable. The explanatory variable is the amount of resistance training, and the response variable is the number of hospital visits. So in this study, we're going to think of it that way, that we're going to look at how does the intervention of resistance exercises influence the hospital visits. Okay. And so here, when I plug and copy and paste that data into the linear regression app, I get this graph with this data over here. And so I can see that there's this downwards trend, so that the more hours of resistance training they do, the less visits they have. So that seems to be what the trend is here. So it's moderately positive. I'll talk about why that is in a moment. Negative linear relationship between hours of resistance training and hospital visits. I don't really see any outliers. I know there's this point up here, but we can do the outlier test on the X values and the Y values. That's why they give you this stuff here. I'm not seeing an outlier. Like if I saw a patient here who did like hundreds of hours of resistance training and had a lot of hospital visits, and maybe that would be it. Or if I saw an outlier like way out here of one person that did 500 hours of resistance training, that might be an outlier there. Okay. So let's interpret the correlation from that previous slide. We have this correlation of negative 0.619. So just the correlation coefficient tells us two things. It tells us the direction and the strength. So I would say that their negative 0.619 is pretty moderate. I'd say it's moderately strong. Usually if it's kind of like close to 0.6, 0.7, I start to say that's on the stronger side. If you get 0.8, 0.9, it's definitely strong. Linear relationship between hours of resistance training and hospital visits. Now, the coefficient of determination is the percent of variability in Y that can be attributed to a linear relationship with X. So here, right here, we want to, anything where there's an underline, we want to change that based on the context. So here in this case, that coefficient of determination, this 38.3% from the app, tells us that 38.3% of the variability in the sample's hospital visits can be attributed to a linear relationship with resistance training hours. So there's obviously other influences if we wanted to develop some type of multivariable model instead of just looking at one factor and how that contributes to hospital visits. There's lots of other factors, right? Diet could play a part. Other sorts of exercise could play the part. So there's other variables that we might want to explore. Okay. And so here we have our output. Let's interpret the slope. Recall that the slope means that Y is predicted to increase or decrease, depending on increase if the slope is positive, decrease if the slope is negative. Slope Y units per X units. So our slope here is negative 0.0613. You can see it right here, or you can see it in this box here. Okay, negative 0.0613. And so the number of hospital visits is predicted to decrease 0.0613 visits per hour of resistance training. All right. Now let's interpret the y-intercept. So we see the y-intercept right here. It's also down here. The estimate of the y-intercept is 11.16. So recall that the y-intercept is a predicted value when x is 0. So if I wanted to use the sentence, when there are 0 hours of resistance training, the predicted number of hospital visits was 11.16 visits. Basically, that's like an average for the people that had 0 hours of resistance training. Okay, so again, each of these underlined words should be replaced when you write your own sentence. That's a good way to get a good sentence if you just think about replacing those words. I'm not saying you have to word it that way, but you're going to include all the details if you kind of use this guide that I'm giving you. Okay, now we can use our equation to predict the regression model, to predict how much hospital visits someone who's done 30 hours of resistance training has done. I copied this here. The resolution wasn't awesome, but I copied this. And so I want to figure out 30. So right here for this X, I'm going to do 30 times 0.0613 and subtract that from 11.2. I used a calculator and I got 9.361. So on average, someone who does 30 hours of resistance training is expected to visit the hospital about 9.361 visits. It's a theoretical prediction, so it doesn't have to be a whole number, but it's about 9 visits, right? Somewhere between 9 and 10 visits, someone that does 30 hours of resistance training. Okay. Now, if we look at the previous prediction, and we're told that the residual was negative 3.361, so I randomly pick someone and see that they exercised 30 hours, and that person has a residual. What is the residual? The residual is the difference between how much they actually went to the hospital minus predicted amounts of hospital. So if we look at this, the residual, negative 3.361, the actual I don't know, but I know that their predicted number of visits was 9.361. So I'm trying to figure out this actual. I can add this to this side. So I left that space there so I could add it to this side. And if I move this over here by adding it, then I'll get the actual. And so I see that their actual number of visits was 6 visits. So the actual number of visits for this patient that did 30 hours of resistance training is 6 visits. If the residual was positive, I could just add that to my predicted amount. If it's negative, I could subtract it from the predicted amount. That's one way to think of it, but I set up an algebra equation too. You don't need algebra to do this, but that's just how I like to set it up. Okay, and so that's an example of going through everything that we can do with the output of a linear regression test for this skill. Okay, here's some other examples where we're looking at how the temperature changes and the number of firefighters needed. Here I see that there's a pretty weak evidence of a linear relationship. This does not look very linear to me, but it is positive. It's just very weak. And so I would say this is a very weak linear correlation between those values. And if I look at the slope right here, the slope right here of 0.0852, it says that the number of firefighters increases by 0.0852 per degree in temperature increase. So that's not a very huge amount. It's pretty close to 0. It's basically saying there might be a little relationship there, but there's lots of other variability that has to do with it. Maybe we want to look at the wind or something like that. Now this graph looks at the number of firefighters that go to a fire and the cost of the damage in thousands of dollars. So we see this here, and we look at the correlation, and we see that that is 0.725. And so we go, whoa, that's strong evidence of a linear relationship. It seems like there's a strong linear relationship between the number of firefighters sent and the cost of the damage. Okay, so if I look at the slope right here, the slope, which was $43.92 thousand, it predicts that the cost of the damage increases by $43,920 dollars per firefighter sent. So should we not send as many firefighters to fire? They're causing all this damage. Well, we have to be aware that we're just looking at the mathematics behind this, but we have to think about what we learned in the first unit, that there's other variables that could contribute to this relationship, that there could be a lurking variable there. So the size of the fire, right? The size of the fire will increase the number of firefighters that need to address it, but also increase the amount of damage that is done, which is, these are like $2.5 million in damage. Those are huge amounts, and they will require a lot of firefighters. Okay, so that should help you understand that better.